when theoretical physicist Dr. Michio Kaku made a public appearance in late October, appearing on a televised Newsmax interview. He issued a statement that at first glance might have seemed dramatic, even sensational. He told the audience to watch for it, a seemingly cryptic warning that prompted intrigue and skepticism in equal measure. Yet, beneath the surface of his words lay a deeply scientific observation, one grounded in his extensive understanding of astrophysics, cosmology, and the mechanics of interstellar objects. Kaku was not referring to an ordinary celestial event or a routine astronomical phenomenon. Instead, he was drawing attention to a very specific moment, October 30th, the precise day when the interstellar object known as 3I/Atlas would reach perihelion, the point in its orbit closest to the Sun. For Kaku, this moment represented a potential turning point, a juncture at which observations could reveal extraordinary behavior far beyond the scope of ordinary gravitational dynamics. His warning carried an implicit hypothesis. If 3I/Atlas were to receive an extra burst of energy during this perihelion passage, an acceleration that could not be accounted for by gravity alone, then the implications would be profound. Kaku's assertion that such a deviation might indicate that we are being visited instantly caught the attention of a small but highly engaged subset of the scientific community, as well as enthusiasts in the broader public interested in the mysteries of space. While casual viewers might have dismissed his statement as theatrical, the reality is that Kaku's expertise lends considerable weight to the observation, and his phrasing was carefully chosen to highlight the possibility that 3I/Atlas could exhibit non-natural acceleration patterns that challenge conventional astrophysical explanations. In essence, his comment was not a prediction made in isolation, but a call to watch an object whose behavior could have implications for our understanding of interstellar physics, and perhaps even the presence of phenomena that we have yet to fully comprehend. As the calendar turned to late November, the data regarding 3I/Atlas began to clarify the picture in a way that was both surprising and scientifically significant. Observations confirmed that the object had indeed received an additional energy boost around the exact perihelion date identified by Kaku. This confirmation came from NASA's JPL Horizon system, which tracks the positions and trajectories of celestial objects with high precision. According to the data, 3I/Atlas experienced a non-gravitational acceleration term of approximately 1.6 x 10⁻⁻⁶ astronomical units per day squared on October 30th. To understand the magnitude of this figure, it is necessary to translate it into more tangible terms. This acceleration equates to roughly 0.05 millimeters per second per day. At first glance, this might appear insignificant, almost negligible. However, in the context of celestial mechanics, even such a minuscule force, applied consistently over time, can produce observable deviations in an object's trajectory, resulting in a path markedly different from predictions based solely on gravitational influences. As subsequent analyses continued, the observed non-gravitational acceleration remained present, although updated modeling reduced its magnitude slightly to 4 x 10⁻⁷day, caret 2, by November 24th. Despite the reduction in value, the crucial point is that the presence of anomalous acceleration remained indisputable. This continued deviation has forced astronomers and trajectory analysts to reconsider their calculations and re-examine the assumptions underpinning their models. The ongoing adjustments in JPL's trajectory solutions highlight the complexity of accounting for forces beyond gravity in predicting the movement of an interstellar object, especially one exhibiting behaviors that challenge the conventional understanding of cometary physics. Under the standard cometary model, non-gravitational accelerations are typically attributed to the phenomenon of outgassing. As comets approach the Sun, the increasing heat causes volatile substances, such as water, carbon dioxide, or carbon monoxide ices, to sublimate. The process of sublimation generates jets of gas and dust that escape from the comet's surface, producing reactive forces that can slightly alter its trajectory. These sublimation-driven forces are well studied, and their effects are routinely incorporated into models used to predict cometary motion. In most cases, the magnitude and direction of these forces can be estimated with reasonable accuracy, allowing astronomers to correct for non-gravitational influences when calculating orbital paths. However, 3I/Atlas presents an intriguing challenge. While the observed non-gravitational acceleration could, in theory, be explained by outgassing, the magnitude and duration of the acceleration do not align neatly with the quantities or distribution of volatiles typically observed in comets. For a comet of its estimated size and composition, the acceleration would require a level of outgassing that is inconsistent with observations of its physical characteristics, such as brightness variations, tail formation, or the presence of a detectable coma. In other words, if conventional outgassing were responsible, it would need to be unusually intense and sustained in a manner not typically observed in known cometary bodies. This discrepancy has forced analysts at JPL to repeatedly revise their trajectory solutions as new observations become available, emphasizing the difficulty of reconciling the data with standard cometary behavior. The implications of this anomaly are both scientific and philosophical. From a scientific standpoint, it suggests that our understanding of small body physics and the mechanisms driving interstellar objects may be incomplete. It opens the door to the possibility that there are unknown physical processes or material compositions at play, which could manifest as non-gravitational accelerations not easily explained by current models. For example, the composition of 3I/Atlas could include exotic ices or materials with properties that react to solar radiation differently than the standard water ice and carbon dioxide mixtures found in ordinary comets. Alternatively, the distribution of these volatiles might be highly asymmetric or concentrated in unexpected regions, producing jetting behavior that defies typical predictions. On a broader level, Kaku's initial suggestion that such an anomaly could hint at visitation adds a layer of intrigue that extends beyond traditional astrophysics. While the term visitation inevitably evokes notions of extraterrestrial intelligence in popular culture, the underlying scientific question remains grounded in observation. What mechanisms could produce a measurable, persistent, non-gravitational acceleration in an interstellar object? Until the precise cause is identified, the object serves as a compelling reminder of how little we still understand about the dynamics of bodies traveling between star systems, and it underscores the importance of high-precision monitoring and modeling in modern astronomy. In practical terms, the study of 3I/Atlas and its unusual acceleration presents opportunities for expanding our knowledge of interstellar objects in ways that were previously theoretical. By combining high-resolution observations, sophisticated modeling, and comparative analysis with other known comets, astronomers can begin to probe the limits of current theories. Each adjustment to the object's predicted trajectory provides valuable information about the forces at play, allowing researchers to refine models, test hypotheses, and explore potential alternative explanations. Moreover, this ongoing analysis strengthens the scientific methodology itself. Anomalies like 3I/Atlas force scientists to question assumptions, rigorously validate models, and embrace the uncertainty inherent in studying phenomena at the edge of our observational capabilities. Ultimately, the case of 3I/Atlas serves as a striking example of how even small deviations in motion can have outsized significance when observed in an interstellar context. The data from NASA's JPL Horizon system and subsequent analysis underscore that the object did not behave entirely according to expectations dictated by gravitational forces alone. This anomalous acceleration challenges our conventional understanding of cometary physics and invites continued scrutiny, observation, and debate. It also highlights the value of expert voices like Dr. Michio Kaku's, whose foresight and willingness to articulate unconventional possibilities can draw attention to critical moments in astronomical observation. While the precise cause of 3I/Atlas's extra energy remains under investigation, the implications for science and for our understanding of interstellar phenomena are undeniable. In conclusion, the story of 3I/Atlas is more than just the narrative of a small object hurtling through space. It is a case study in the importance of careful observation, rigorous modeling, and openness to unexpected phenomena. From Kaku's public warning to the confirmation of non-gravitational acceleration, the unfolding events surrounding this interstellar visitor illustrate the dynamic nature of astronomy, where even tiny forces can have profound consequences. As researchers continue to track, model, and analyze 3I/Atlas, each new piece of data brings us closer to understanding the complex physics of interstellar objects and the potentially extraordinary phenomena they may reveal, reminding us that the universe often defies expectations and that careful attention to anomalies can sometimes lead to revolutionary insights.